This video discusses fluids, in particular liquids, and we're going to investigate how pressure is measured and also Archimedes' principle on why things float. So here we have a system that's closed in here inside the bellows, and it responds to outside pressure, creating force, working against the inside pressure. So we have this pressure attached here and creating over an area, creating a force. Pressure is force divided by area. So we can get the force by taking the pressure times the area. So we have a force pushing in on the bellows here. There's an internal pressure inside the bellows that resists that push. Well, it's calibrated, and we have a indicator here showing on the scale. So an example of how to measure pressure. We're not going to work the details of the calculation of how that arm swings. Another method would be to observe that when we have a tube with a liquid inside and we're open on both ends to the atmosphere, then we have equal levels for the water or whatever substance we're using inside the tube. However, if we attach one end to an object that has pressure in it, if this object's internal pressure is higher than atmospheric pressure, then we create more of a push on this side, and we observe that the column over on the left that's open to the air, that rises, goes up higher. The atmospheric pressure is not pressing down on the column as strongly as the pressure from whatever that animal is, that balloon. So the height here, h, tells us what this pressure difference is, and we can use the height times the density of this liquid times acceleration due to gravity. I'm more in the habit of writing density times acceleration due to gravity times h. Works out the same and multiplying, and it doesn't matter which factor comes first. But the pressure is rho gh, the density of the material, the fluid, acceleration due to gravity, and the height difference on the two sides. This tells us the gauge pressure of the system. It's not the true pressure of the system because we have this atmospheric pressure we're working against. The true pressure is found by taking the atmospheric pressure and adding on this sort of relative pressure here, the rho gh term. So we have a gauge pressure that is rho gh, measured by the height of the difference, and we have atmospheric pressure. We add those two together, and we get the true pressure inside the system. Over here, we've got our probe attached, just going through the vacuum seal, and less pressure over here now, so the atmosphere is winning in the push of this fluid, and we would calculate the pressure inside the peanuts by subtracting from the atmospheric pressure. As we can see, the atmospheric pressure is higher than the true pressure for the system. So that's an open tube manometer. It measures pressure relative to atmospheric pressure. To get the true pressure, what they call the absolute pressure here, we have to adjust our measurement by the atmospheric pressure. So atmospheric pressure is the sort of calibration point for this device. Blood pressure can be measured. Why do they put the blood pressure cuff around the arm and not the ankle? Well, we get a better indicator of the pressure at the heart by taking the blood pressure at the same level as the heart. There's a rho gh term. Well, it's more complicated going through blood vessels down here, but there is a difference in the pressure at the ankle compared to at the arm. A barometer. Here we have a tube with a sealed end and a vacuum inside, so there's no gas pressure in here. The atmospheric pressure presses down on this mercury and creates a force. The pressure is transmitted undiminished. Pascal's principle tells us that. So whatever the atmospheric pressure is here, we've got that atmospheric pressure existing over here. And this pressure times area would create a force that's able to sustain the weight of this column of mercury. And this pressure, again calculated with rho GH, would be a measurement of the atmospheric pressure. In this equipment, we don't have an opposing pressure that we have to compensate for in our calculations. So we get the atmospheric pressure, rho GH. Rho would be the density of mercury, because that's the working substance indicated in our diagram. We're doing this on the surface of the Earth, so we use 9.8 for the G, and you measure the H, and if you have 76 centimeters of mercury, you're probably near the surface of the Earth. How about Archimedes' Principle? Why do some things sink and why do some things float? This anchor is made of iron, but it sinks. This submarine is made of iron, but it floats. What's the difference? And then balloons, they're floating. It deals with how much water is being displaced, and we'll observe that here. So here we have let's say a cylinder underneath the water. Which side of the cylinder, which part of the cylinder has the greatest force acting on it? Well, the pressure creates force, and the force is found by taking the pressure times the area. We have the same area on the top and bottom of this object. So how will we judge which has the greater force? Force is equal to pressure times area. The areas are the same. Are the pressures the same? And the answer is no. This pressure on the top deals with the distance h1 underneath the surface of the liquid. The pressure for side 2, or end number 2, we have a different h value. It's h2. And this is a bigger number. There's a bigger force here than up here. The difference of these two forces is the buoyant force acting on the object. FB is F2 minus F1. Now this gets a little complicated to calculate, so there's an easier way. The buoyant force is equal to the weight of the displaced fluid. Equal to the weight of the displaced fluid. So you can read about that in the text, or for my students in the reading guide that I've passed out. Again, we have a buoyant force because the pressure on the bottom of the object is greater than the pressure on the top. Pressure is rho GH underneath the liquid. So this buoyant force may or may not cause the object to float. If mg, if the weight is greater than the available buoyant force, then the object will sink. And that'll happen if the object has a density, if we're in water, has a density greater than water. The object will sink. But if the object is less dense than water, then the object will float. Ships made of iron. Why doesn't iron sink? Well, it's in a special shape. There's air inside the hull, and the boat does sink down into the water, pushing water aside, and the Archimedes principle says the buoyant force is equal to the weight of the displaced water. So what must be done, the ship must be designed, built, such that it has a fairly wide bottom. As it sinks a little bit, it pushes aside a lot of water. So a little bit more cargo gets loaded on. The ship will sink just a little bit more, displacing a weight of water equal to the new cargo. So buoyant force is the weight of the displaced fluid. And we can calculate that, the weight of the displaced fluid, with mg, m being the mass of the displaced fluid. And we can get m using the fact that density is mass over volume. Density is mass over volume. So mass would be density multiplied by volume. And we'll do practice problems on that for my students. A device here to measure the density of a fluid. So the blue shaded here, we're in some fluid and liquid. And we have a reading here of 0.87. That would be its specific gravity. That's the density of the liquid compared to water, 0.87. So if we have a denser liquid, why is it that it'll rise up and we get a reading of 0.9 or 0.95? Why is it, if the density of the liquid is greater, this device floats better? Well, Archimedes' principle, the buoyant force is equal to the weight of the displaced fluid. If the fluid is more dense, then this shape will displace an amount of weight of the fluid earlier, before it sinks too far, compared to this reading of 0.87. If the fluid is denser, then we get the required buoyant force, which is just equal to mg of the object, the weight of the object. We get a buoyant force equal to the weight of the object when the hygrometer here sinks just a little bit less into the fluid. Because the fluid we're pushing out weighs more per cubic centimeter, let's say. Because it weighs more per cubic centimeter, has a higher density, then we have a situation where the hydrometer does not need to sink as far. We can weigh objects in water, weigh them in air, and there's a method for calculating the density of the object. It may be an irregular shape, but you can tell if someone has given you a gold coin or a lead coin by doing this measurement. Breathing, we have muscles that work in the diaphragm, and as the diaphragm expands, it lowers the pressure in the lungs and air goes in. We won't concentrate too much on that, and not going to concentrate too much on capillary action, just mention it here. If the tube is wide, then there's a lot of weight in the water that's trying to be pulled up by the adhesion of the water to the side of the glass. If the tube is smaller radius, that adhesive force can lift a higher column of water. Not more water, but a higher column of water. And that's where we're going to end the video. So we have the fact that we measure pressure with gauges. For some of these, the pressure must be corrected because we're working against atmospheric pressure. In other situations, we don't have to correct, like the barometer. The pressure was 0 above the column of mercury. And you might ask yourself, why is mercury a choice for barometers rather than water? Then this video also reviewed Archimedes Principle. The buoyant force is equal to the weight of the displaced fluid. So work some practice problems on your own and ask some questions.